Hello, and in today's video, let's talk about LLM tokenization of numbers and how this impacts arithmetic operations. So this article from Hugging Face came out almost a year ago, but I only just discovered it now, and it's quite detailed and information dense. So let's go through it. At some point in time, there was a question of asking 9.9 or 911, which one is larger, and 911 would sometimes be chosen, I guess, since here you would get 9 tokenized and then 9, and then here 9 and 11, and then maybe the LLM has some arithmetic circuit which is comparing 11 to 9, and then it says it's larger. That's my guess, but of course this is probably fixed now, but we can still extract many lessons from how numbers are tokenized with large language models. So first of all, we're going to discuss the method that Hugging Face uses to compare these. Another interesting thing is how you read the numbers as a tokenizer, because as soon as you have large numbers, you have to split them. And it's a question of, are you reading it from right to left or from left to right when you're splitting them? And then there is a method which is the best of those chosen for arithmetic operations. So we'll find out what that is. Of course, in the GPT-2 paper from 2019, the method that was used was byte pair encoding, and this works good, but not as good as other approaches. It merges frequently occurring subwords, and what this means is that if we take this, can I zoom out here? Yeah. If we take this graph of the heat map for numbers from 1 to 1,000 with the GPT-2 tokenizer, this many words which are blue, are tokenized as 1 token, and then the red ones or the pink ones are tokenized as 2. So you can see, like, of course, numbers that occur less often will have 2 tokens for that word itself, since it didn't occur that many times in the dataset to be merged. And then in 2023, Llama came out, and in their BP implementation, they split all numbers into individual digits. So there were just only 10 tokens to represent any number. And then DeepSeek released a model V2 with the similar tokenizer. And then Llama 3, what did they do? They handled them in groups of 3 digits. So this means that numbers from 1 to 99 each had their own token. And then from 1,000 onwards, they were a composition of these tokens from 1 to 999. And then we have the right to left tokenization. First of all, according to rumors, this is what Claude uses. And what this means is when you're tokenizing this number, for example, and you're using the same group of 3 method, which is used by Llama 3, from left to right, you'll do 1, 2, 3, 4, 5. But from right to left, you'll do 3, 4, 5, 1, 2. Here's a good example which demonstrates the difference. So what you can see is, like, on this carry term, it's kind of awkwardly mapping if you do have a carry 9 and 1 to 80. Whereas here, it's from the least to most significant numbers. So it just seems more natural. And according to Hugging Face, this shift in the tokenization boundary produces additional complexity when you have this 9 plus 1 mapping to 80. It kind of makes sense. There needs to be some specific circuit made within the network when it's training so that it can make this mapping, which is taking more inference compute on the forward pass. And then what does this suggest? It says that right to left tokenization could be an improvement over the standard L2R tokenization used by Llama 3. So that is just like the standard technique, since if you do a regex split, then it's by default from left to right. So that just happens by default. But if you want it to do right to left, then you have to have a separate regex split pattern, which we'll see. And now let's just go over what we discussed. So we have GPT-2, just pure BP, no special handling of digits. Then Llama 2 and DeepSeek, as well as Llama 1, I guess, just did single digits, 1 to 99 for Llama 3, and then R2L for Claude, ? And this was a year ago. So these methods have likely been improved since then, but that was the state of the tokenization scene at that point. So they actually test this with a bunch of methods. One thing that's interesting is they are training models from scratch. They're only 1.5 billion parameter models, but nevertheless, it's impressive the effort they put into measuring the tokenizers and literally training them from scratch. This is done so that they all have the same data mixture and roughly an equal compute budget. And then this means that the only meaningful difference is just the tokenizers themselves, and it'll be somewhere else, but some tokenizers have larger vocabularies. So in order to have the number of parameters be equivalent, for those tokenizers that have larger vocabulary, they either decrease the hidden size or the number of transformer layers, I forget which, to equalize on that front. Okay, so further on, we picked 3 tokenizers mentioned previously. So GPT-2 BPE, Llama's 3-digit, and DeepSeek single-digit tokenizer. And interestingly, to test R2L tokenization, they created just a R2L version of the BPE and 3-digit tokenizer with minimal changes, where the number would be chunked into groups of 3 digits from the right side before being tokenized. They did not create a right-to-left version for the single-digit tokenization, since it would produce the same result, right? Since tokenizing from left to right or right to left, if they're all just single-digit, it doesn't matter at all. It's as soon as you have groups that defining the group boundary is different based on which side you start from. And literally, this is all the extra processing that happens. So first of all, you can see for Llama 3, it already has this regular expression split, which is standard. So you're splitting on these word endings as well as numbers. What else is here? A bunch of arithmetic stuff that I'm not able to interpret it on the fly. And then here you do have the pattern split. So split by R2L digits, you're finding any group of 3 digits and you're matching to those. And then this is if there's any digits on the left of that group, if I'm not mistaken, of size 1 to 3. Because your last group of digits on the very left could be like of size 2 or size 1. And this is what I was mentioning. So the models they use are just the original Llama architecture. You can see like they just load the Llama tokenizer in this case. But to account for the differences in the tokenizer size, they modify the number of hidden layers so that each model has roughly the same number of parameters, 1.45 billion. And this is just an example. So you have the visualization of an embedding matrix, which is simply the vocab size times hidden dimension, such that when you embed this vector based on whatever sequence you have, right, you'll get sequence times vocab size times hidden size, and then the final tensor that will go through the network is just of size sequence and hidden dimension, since the inner dimension of this matrix will just fold in the dot product. So what do they say here? For a fixed number of trading tokens, Model B learns more due to its larger embedding matrix. To maintain a constant compute budget, they reduce the number of hidden layers in those models with larger vocabulary. So I'm not sure, which one would be higher. Maybe the Llama tokenizer with the 1 to 999 special tokens, and then the compositions after that, since it was trained later. Or actually, I guess the latest trained model in this entire test was DeepSeek v2. And my hypothesis would be that the BP tokenizer is the smallest, because GPT-2 was from a while ago. Here's their pre-training data. You can see that they have algebraic tasks, math. I assume FineWeb would just be, let's look at it. We have the ability to do that. It is data about just the finest collection of data the web has to offer. And this one says 18.5 trillion tokens, which is insane, 108 terabytes. But right here, it's only 120 billion tokens. So they're only taking a subset of the data, because did they say 100? 18 trillion, right? So we're talking 2 orders of magnitude larger, but this is only 120. Yeah, so what I'm saying is that FineWeb is 2 orders of magnitude larger than the number of tokens. Of course, if you're training 1.5 billion parameter model, then you're kind of crazy if you're using that many tokens. That would just be extremely inefficient and probably overfit. So makes sense, but they don't mention that it's a subset, even though it is. And then what they say here is that for evaluation, of course, it's non-deterministic, since you initialize your weights essentially randomly varied from 0. At least that's probably what they did. And what this means is that even if you have the same data, the same architecture, the same compute, then you can still get different models at the end due to noise. So what they did is that they trained 3 additional models with the tokenizer that produce the highest variation in model scores on the same data mixture using different seeds. So all we can see is that, they have, in this case, 4 models, if I'm not understanding correctly. So instead of 3, and this is for the 3-digit L2R, 3-digit R2L, and pure BP tokenizer models. So I assume that these were the 3 noisiest tokenizers. So what they don't have here is the single-digit tokenizer, if you notice or if you pay attention. And then they have 2 types of evaluation. Word-based problems, the reason for this is that they have small models, so you can't do crazy arithmetic with just pure numbers, or else they'll just fail. But you can do simple arithmetic with pure numbers. So they created, because of this, a custom benchmark with addition, subtraction, multiplication, and division. And they are split across various axes, which allow to perform a more detailed assessment of the pitfalls of LLMs when doing math. And the splits of the data are based on difficulty, whether it's a float or int, whether or not commas were used to demarcate digits in groups of 3, and the operation itself. One other thing to note is that they use something called the quasi-exact match, QEM, of the answer, which means that if it's 127.60 is what the model gave, and the answer is 127.6, that's fine. And also, as it should be the case, 1234 and 1000,234 is the same thing. So let's look at the results. Here we can see that single-digit tokenization outperforms all other tested tokenizers in arithmetic problems. So for integers and float, what you will notice is that each model is on a proportional level the same versus whether it be integer or float. They have this much better worded here. Essentially, the optimal tokenizer for integers is also the optimal for floats, and single digit is the best. Then now let's look at it based on operation. We can see once again that for all of the 4 types, single digit is still the best, but then right to left is better than left to right. So once again, it's more intuitive, since one thing worth noting is that when you do addition on your own, you're also doing it right to left. You're not doing addition from left to right. That doesn't make sense. One thing that is different, though, is the 2-digit addition, for some reason, is better with the R2L approach, even though these shouldn't be, these 2 tokenizers shouldn't be different unless I'm missing something, since the right to left and left to right paradigm only applies as soon as you're beyond 3 digits. And then another thing worth noting is when you have 1 digit, right? BPE, 3-digit L2R, 3-digit R2L, and single digit will all just tokenize them as single digits. You can't tokenize a digit in anything that is more granular than the digit itself. So although these results aren't extremely varied, it's still interesting that you're 4% worse with BPE versus the single digit tokenizer. I suppose that since there are no other tokens being trained for numbers, there is more capacity to train mathematical circuits through single-digit numbers, since there's only 10 ways to represent numbers, as opposed to the BPE tokenizer, where you have to have probably a circuit which is calculating 21 plus 3 or something. Whereas you just have this really massive circuit that looks like an ALU probably, and has just all of these, only has 10 inputs, and it's kind of just routing these in a convoluted way. But there's only one circuit as opposed to many different ones when you have VP. I hope that makes sense. All this is to say that the single-digit tokenizer on the whole performs better. Let's see what other things they say about the analysis. 3-digit R2L tokenization has better performance over standard 3-digit L2R tokenization. So essentially, reading from right to left is better. The only thing that it isn't better at is multiplication, but everything else you can see that right to left, which is blue, is noticeably better, 4%, I guess, in this case. I want to see what else we missed. Well, it's intuitive to assume that integer problems will have better performance, which is confirmed by the results. They have the performance gap is similar across all tokenizers. So essentially what we just said, the optimal tokenizer for integers is the same as floats. And what's set up here is that while the difference for easier problems are less pronounced, as the complexity of the problem increases, there's an increasing gap between the best tokenizer and the rest. So in this case, when we come to number of digits, for one digit, once again, it's not that crazy because they all tokenize the same. But as soon as you get to 5 digits, then you have like a 9% difference. In this case, it's even 12%. It's a bigger difference. But generally, as you go down, then the difference between the best and the worst increases. And even here, for 2 digits, the best one is not even single digit. So that's that. Another thing worth noting is that the pure byte pair encoding tokenizers show inconsistent performance when numbers are chunked in groups of 3 from right to left. And evidently, pure BP tokenizers without any additional number processing don't really benefit much from R2L to begin with. So a possible explanation of why this right to left structure is causing inconsistent performance is that there's now a lack of structure in how digits are grouped together in these tokenizers. I guess since you're enforcing something which the model didn't learn through the merges, that's my guess. And unlike the 3-digit tokenizer, due to the particularities of BPE, there are other numbers that are also grouped less consistently. So this inconsistency undermines the advantage of right to left tokenization, which works best when numbers are uniformly tokenized in 3-digit chunks from at least the most significant digit. This makes sense, right? Because you're not guaranteed to get a 3-digit chunk with BPE. So what this means is, I guess from right to left, there's just less structure for the model to grasp when it's trying to perform arithmetic operations. When it comes to word problems, when you smooth it out, you can see that they're all pretty much the same. The only thing worth noting is, what did they say? Well, let me first show you, it is kind of noisy, so don't really take this, don't take this data as like the gold standard. Kind of isn't statistically significant from what I can see. And they even mention it that it's less pronounced in word-based problems. They do see that the single-digit and 3-digit tokenizers generally outperform the BP-based tokenizer. So I assume red is BP, yeah, that's right. And then the other three, the best one being left to right, interestingly. And then R2L and single-digit being below it. Perhaps since left to right is the most common method based on the fact that it was used since the beginning, this could somehow mean that since word problems are trained quite often, since it's text-based, that they have some time advantage since they've been trained more on it. But I'm just kind of speaking out of my butt at this point. Now, let's talk about the bonus, right to left inference on Llama 3. One of the other things that they wanted to test was how adding a tokenizer that the model was not trained on would affect performance. So what they did is, without having to retrain or fine-tune it, they swapped the standard left to right tokenizer with the right to left tokenizer for inference. And what's one important thing to note is that when adding two numbers in a 3-digit tokenization scheme, the result can sometimes produce more tokens than the input numbers. So one such example is that when you add these two numbers, you get 1110. And this is just to say that they call this carry additions, where you do get an additional token or additional number, a digit, and then without carry where you don't. And they wanted to explore in particular how much a difference this makes when performing the two separate types of addition, since the hypothesis is that right to left addition helps in particular when there is a carry. And you actually see this, it's really amazing. So there's two different things. First of all, overall, right to left tokenization is better in addition tasks, and more interestingly, even though we didn't train it with that tokenizer. So although swapping out this tokenizer shouldn't really affect anything, because at the end of the day, the atomic units, the numbers are the same, it's still kind of interesting to me that the tokenizer that you didn't train on is better for arithmetic. So you can see right to left is almost always above, but this does not look statistically significant. But look, none of these are with carry, so it doesn't really matter. And what's the number on the x-axis? This is the number of digits. So I'm honestly amazed that it's able to do 20-digit addition. I had no idea that transformers could do this with 50% accuracy. That's not bad. That's probably higher accuracy than a human if you're considering that, you have to do a massive addition on paper if there's 20 digits. But then if you come to the carry, you can see an amazing difference as the number of digits increases, but a weird sinusoidal arc where, like, for some reason at 18 digits, right, left to right is better than right to left, which doesn't make sense. But then when you get back to here at 20, you have 57% versus 17%, so 40% difference. So let's see what they noted here. For non-carry additions, they're talking about something with digits that are multiples of 3. Honestly, I didn't really think that's too significant. But then you do see a cyclical trend for every 3 digits when comparing L to R and R to L carry additions. For multiples of 3, left to right slightly outperforms right to left, but in the next digit, right to left performance shoots up and overtakes left to right, further widening the performance gap in the digit after that before dropping again. After that before dropping again in the next multiple of 3. That's kind of poorly worded. And what else? They found that the model's output token perfectly formatted numbers as right to left with just a few right to left examples, despite being trained on left to right formatted numbers. So I think they actually did a 5-shot example for, 5-shot questions. So they must have given it like 5 examples and then asked the question. One thing is that this is super important because it shows that these models just aren't memorizing patterns from the training data. When you give it an entirely new distribution of right to left number tokens, it was still able to reason and perform even better than the data it was really trained on. So that is kind of cool. And then when averaging across all digit lengths and carry settings, there was the overall 10% improvement in accuracy over the standard left to right tokenization using Llama 3 just by swapping out the tokenizer with a few lines of code. And you can see that from 70, you pretty much get to 80 with right to left tokenization. They did a similar experiment with single digit tokenization, but performance dropped off really quickly after a few digits. This makes intuitive sense since the shift in token distribution of the training data and single digit tokenized data is way larger than the difference in token distribution between the training data and the R2L data. So first of all, I'm not really sure what they mean by single digit tokenization because once again, for single digit tokenization, right to left and left to right don't really make sense. Maybe they're saying they wanted to compare this as a third method, and they're saying that as you increase the number of digits, well, it's not scaling well because you just have linearly amount of digits as you increase, whereas like it's also linear if you're doing right to left and left to right with a group of 3, but it's a linear divided by a factor of 3. So you're still having less tokens. And since we're not talking about like complexity analysis here where you're in the millions, since it's just like these small numbers, the divided by 3 factor there actually does count, have an effect. So let's look at the conclusions. First of all, while BPE remains a popular tokenization method, you need pre-processing steps. I think they mean post-processing, but pre-processing before it's given to the transformer to fix the inconsistencies and improve numerical reasoning. If you have to use a tokenizer that has a token for numbers up to 3 digits, make sure you tokenize your data right to left. And you can just do that with the code snippet above where they have that regex expression that takes those groups of 3 before you apply the general one and then splits up the digits that way. Amazingly, if you have a model that is already tokenized with the left to right tokenizer, you can get better math performance by running it with a right to left tokenizer at inference. And it's kind of just like free lunch. So do that and it shows the reasoning capacity of models. Word-based problems have less apparent performance differences between tokenizers, but they found that single digit and 3-digit tokenizers do outperform BPE. So as soon as you put stuff in words, then yeah, there's less of a problem since these tokenizers are all pretty good at tokenizing words anyways. And then most importantly, for arithmetic operations, single digit tokenization has significantly better performance than other methods. And you can see here, it is pretty significant, 35% versus 30%, 25, 25. In conclusion, the work here shows that tokenization can be improved. Tokenization has a significant impact on the arithmetic performance. And with careful selection, they can improve the performance based on the tokenization strategy. That is everything for the article here. This is, I guess, an explanation of how single tokenization doesn't matter because it's 1, 2, 3, 4 or 4, 3, 2, 1. Either way, it gives the same number. And yeah, I hope this was informative. If you don't like reading, then this video is for you, and have a nice day.